Two particles at opposite ends of space share a single, invisible thread. This is quantum entanglement, the phenomenon Albert Einstein called spooky action at a distance. It defies the cosmic speed limit of light, linking the fate of one particle to its partner instantly, no matter the distance between them. By the end of this journey, you will understand how this bizarre quantum link evolved from a scientist's nightmare into the engine of a technological revolution, powering everything from unbreakable codes to computers that think in possibilities. Why did the greatest mind of the 20th century reject this idea so forcefully? And what secret about the fabric of reality did his rejection ultimately reveal? How can a connection that seems to ignore space and time become the cornerstone of our future? The answers rewrite our story of the universe. What does it mean for two things to be truly separate? The Quiet Study in 1935 was a fortress of classical thought. Albert Einstein, alongside Boris Podolsky and Nathan Rosen, crafted not a celebration of the new quantum world, but a brilliant trap. Their paper, known by their initials EPR, was a challenge thrown at the feet of the quantum establishment. It was designed to prove with elegant logic that the theory was incomplete. Their weapon of choice was the very phenomenon we now call entanglement, though they saw it as a ghost in the machine. They argued that if measuring one particle here instantly determined the state of its partner far away, it meant one of two things. Either information was traveling faster than light, shattering Einstein's own theory of relativity, or the particles possessed definite, pre-existing properties all along. Since faster-than-light communication was unthinkable, they concluded the second option must be true. There had to be hidden variables, unseen details the quantum equations missed that predetermined a particle's fate. This belief is called realism, the comforting idea that objects have definite properties whether we look at them or not. The moon is there with a specific location, even when no one is watching. Einstein, Podolsky, and Rosen applied that same common-sense logic to the quantum realm. They framed their argument as a paradox, a contradiction that revealed a deeper truth. By measuring, say, the position of one entangled particle, you would know its partner's position with absolute certainty without ever touching it. They reasoned this knowledge proved the partner's position was a real, independent fact, not some fuzzy probability waiting to be born. It was a devastating critique. It painted quantum mechanics as an incomplete story, a statistical approximation of a deeper, more orderly reality. This challenge, what we now call the EPR paradox, forced every physicist to pick a side. Do you abandon locality, the rule that nothing influences anything else faster than light can travel? Or do you abandon realism, the idea that things have definite properties on their own? For Einstein, the choice was clear. He famously insisted that God does not play dice with the universe. He believed in a cosmos of certainty, not chance. The spooky action was to him proof that the dice were loaded, that hidden variables were the unseen hands guiding the roll. This set the stage for a philosophical war that would simmer for decades. But every great paradox demands a resolution. The question shifted from who was right to how could we possibly know? How do you design an experiment to test the nature of reality itself? The answer would not come from thought alone, but from a blueprint for a real-world test, one that would turn philosophy into measurable light. While Einstein saw a universe of hidden certainties, his greatest intellectual rival saw a world of shimmering potential. Niels Bohr, architect of the Copenhagen interpretation, met Einstein's paradox not with a defense, but with a revolution in perspective. Where Einstein demanded a moon that existed independently in the darkness, Bohr proposed a moon whose very location and motion remained an unresolved question until someone, or something, looked up and asked, Their legendary debates were less a clash of equations and more a battle for the soul of reality itself. Bohr's central tenet was complementarity, the elegant and unsettling idea that a quantum object cannot reveal all its classical faces at once. It is like a coin spinning in mid-air. Ask it to be heads or tails and it will oblige, but in that moment you lose all knowledge of its spinning motion. The coin possesses both qualities, but you can only access one complementary view at a time. Bohr applied this to particles. They do not secretly have a definite position and momentum waiting to be discovered. Those properties are undefined, existing in a fuzzy cloud of possibility until a measurement forces a choice. This is the principle of superposition, where a particle exists in all its possible states at once, a ghostly blend of here and there, up and down. So when Einstein pointed to the spooky link between entangled particles as proof of hidden information, Bohr saw no spookiness at all. He argued the two particles were not separate entities sending signals. From the moment they were linked, they were a single, indivisible quantum system, a unified whole even when separated by light years. Measuring one particle did not send a message to the other. It simply collapsed the shared wave function of the entire system, instantly defining the properties of both. There was no signal to travel because there was no separation to bridge. This was a complete surrender of locality, accepting that influence could be instantaneous and non-local, but it preserved a different kind of logic. In Bohr's view, it was meaningless to talk about what the distant particle was doing before its partner was measured. The question itself assumed a reality that did not yet exist. This interpretation places the act of observation at the very heart of existence. It suggests that by measuring, we are not just discovering a pre-written script, we are participating in writing it. The observer is entangled with the experiment. This philosophical upheaval was, as Bohr himself admitted, profoundly shocking. It traded Einstein's comforting, clockwork universe for one that was fundamentally probabilistic and participatory. Entanglement was no longer a bug in the theory, but a core feature, the ultimate expression of this quantum wholeness. Yet for all its intellectual power, the Copenhagen interpretation offered a way of calculating, not a mechanism. It described what happened but remained silent on how. This left a door open. Could there be a more complete description, one that restored both locality and realism? The debate had reached a stalemate of pure thought, two brilliant but incompatible visions of the cosmos. To move forward, science needed to stop arguing and start building. It needed a device, a physical experiment clever enough to ask the universe a direct question and force it to choose an answer. For nearly 3 decades, the great debate remained just that, a beautiful argument without a judge. Then, from an office at CERN where he focused on particle accelerators, a soft-spoken Irish physicist named John Bell found a way to turn metaphysics into mathematics. In his spare time, Bell pondered the EPR paradox with a unique clarity. He asked a devastatingly simple question. What if Einstein was right? What if there were hidden variables, those secret instructions determining a particle's fate? And what if they obeyed the sacred rule of locality, meaning no influence could travel faster than light? If that comforting, classical picture were true, Bell realized it would impose strict limits on how correlated measurements of entangled particles could be. He translated this limit into a set of mathematical boundaries now known as Bell's inequalities. Think of it like a budget for coincidence. In a local, realistic world, the correlations between distant measurements could only be so strong. They had a spending limit. Quantum mechanics, with its spooky, instantaneous connection, predicted correlations that would blow right past that limit. It was an overdraft on reality's bank account. Bell's theorem, published in 1964, was the blueprint for a cosmic courtroom. It stated, with brutal elegance, that no theory of local hidden variables could ever reproduce all the predictions of quantum mechanics. The universe had to give up one or the other. As Bell himself put it, if a hidden variable theory is local, it will not agree with quantum mechanics, and if it agrees with quantum mechanics, it will not be local. You could not have both locality and realism. It was a forced choice. To make this concrete, imagine a simple experiment with entangled photons, particles of light. We can measure their polarization, which is like asking each photon a yes or no question about its orientation. In a local hidden variable world, each photon carries a secret list of answers for every possible question we might ask, determined in advance. When we compare the answers from many pairs, the pattern of agreements and disagreements will stay within Bell's calculated limits. But quantum mechanics says the photons have no predetermined answers. Their properties are born at the moment of measurement, linked instantly across space. This leads to a pattern of correlation so tight, so synchronized that it shatters the local budget. It violates the inequality. Bell provided the recipe. He gave experimental physicists a clear numerical target. They no longer had to argue about philosophy. They could build a machine, collect data, and ask the universe to vote. The quest was no longer about who had the better interpretation, but whose prediction matched the cold, hard numbers. A quiet theorist had handed a weapon to a generation of experimenters, and the race to build the perfect test was on. What would it take to build a machine precise enough to catch reality in a lie? Bell's theorem was a gauntlet thrown down, but the laboratory floor was a messy, unforgiving place. To test the nature of reality, you first had to build a machine that could see it. In the early 1970s, a young physicist named John Clauser took up the challenge, armed more with stubborn determination than with funding or widespread support. Many in the field saw testing Bell's inequalities as a fringe pursuit, a philosophical sideshow. Clauser, working with Stuart Friedman, constructed an experiment of beautiful, if rudimentary, ingenuity. They used a lamp to excite calcium atoms, which then emitted pairs of entangled photons. Their detectors were simple, their measurements painstakingly slow by today's standards. Yet when they compiled the data, the correlation between the photon pairs was too strong. It violated Bell's limit. The universe had spent beyond its local, realistic budget. This first result was a tremor, not an earthquake. It suggested quantum mechanics was right, but critics were quick to point out the cracks, the loopholes. The most significant was the locality loophole. In Clauser's setup, the measurement settings for each photon were fixed in advance. A skeptic could argue that if some hidden signal traveling at or below the speed of light could have coordinated the particle's behavior, local realism might still be saved. It was a slender thread to cling to, but it was enough to keep the debate alive. The baton then passed to a French physicist, Alain. In the 1980s, his team engineered an experiment of elegant cunning. They designed a system where the choice of which property to measure on a photon was not fixed. It was made randomly by a fast switch after the entangled photons had already begun their journey to the detectors. The switch flipped faster than a light signal could possibly travel from one measuring device to the other. This was the crucial move. By changing the question while the photons were in flight, Aspect slammed shut the locality loophole. Any hidden signal would have had to travel faster than light to keep up, violating Einstein's own relativity. The results were unequivocal. The Bell inequalities were violated with stunning precision. As Aspect later reflected, it was a profound pleasure to see an abstract idea become a concrete fact in the laboratory. Reality had voted, and it voted for spookiness. The message was clear. There were no hidden instructions being passed secretly at the speed of light. The connection was instantaneous and non-local. Yet for some, the escape routes were not all closed. Another concern lingered, called the detection loophole. What if the photons their instruments captured were not a fair sample? What if only certain types of entangled pairs made it to the detectors, creating a biased view that mimicked quantum correlations? Closing this loophole would require even more sensitive technology, capable of catching nearly every entangled particle in the act. The journey from theory to proof was a story of human ingenuity chipping away at cosmic mystery, one loophole at a time. But if locality was truly dead, what strange new understanding of the universe did that force upon us? The laboratory walls were no longer enough to truly corner reality. Scientists realized they had to take the experiment outside, using the cosmos itself as their laboratory bench. The final, most subtle loophole was not about detection but about choice. What if some hidden variable, some event in the distant past, had predetermined both how we would set our instruments and how the particles would respond? This freedom of choice loophole was the last refuge for a stubbornly local universe. To close it, you needed a source of randomness so ancient, so disconnected from human will, that no possible conspiracy of hidden variables could account for it. The answer was written in the night sky. Teams of researchers turned their telescopes toward stars hundreds of light years away. The faint photons from these distant suns had begun their journey to Earth long before any entangled pair in the lab was even created. In a breathtakingly poetic maneuver, they used this ancient starlight as a cosmic random number generator. The color or arrival time of a single stellar photon would decide, in that instant, how to measure its entangled counterpart back on Earth. Since the star's light left its source millennia ago, no hidden variable scheme concocted at the creation of the lab's particles could have known about this specific future choice. The universe was being used to interrogate itself. One researcher captured the profound elegance of it, noting they were using the cosmos as a source of randomness to test its own fundamental rules. These cosmic bell tests, spanning continents from Austria to the Canary Islands, created conditions of such immaculate separation that the results became almost metaphysical in their clarity. The Bell inequalities were violated again and definitively. In a parallel and equally human-centered approach, the Big Bell test in 2017 took a different route to cosmic randomness. It harnessed the unpredictable whims of human consciousness. Thousands of people around the world played a fast-paced online game, generating a chaotic stream of zeros and ones. This living, global pulse of free will was fed directly into the settings of quantum experiments on multiple continents. If human choice is truly free, even in a limited sense, then its output is also free from any predetermined cosmic conspiracy. The results from both the stellar and the human tests converged on the same undeniable truth. There is no local, realistic story that can explain what we see. The spooky action is not a theoretical curiosity. It is a feature of our world as real as gravity. This leaves us staring at a profound and beautiful mystery. We have proven the link exists, but we are only beginning to grasp its nature. What exactly is this connection that operates outside the familiar confines of space and time? It does not transmit energy or information in the classical sense, so it cannot be used to send a message faster than light. Instead, it seems to be a fundamental statement about relationship. Two entangled particles are not truly separate objects. They are two aspects of a single, unified quantum state, a whole that transcends physical distance. Measuring one does not change the other. It simply reveals a property of the whole system, instantly defining both ends of the connection. It is as if the universe maintains a single, non-local entry in its ledger for the pair, and our measurements merely read out what it says. This forces a radical shift in how we view reality. The cosmos may be less a collection of isolated things and more a vast, interconnected web of correlations, where what happens here is intimately linked to what happens there, not by wires or signals, but by the very mathematical structure of quantum possibility. This leaves us with a beautiful but often misunderstood reality. The link of entanglement is not a secret wire, nor a faster-than-light signal you could use to send a message. Think of it instead as two dice created together in a single act of magic. If you roll one and see a 6, you know instantly, with certainty, that the other die also shows a 6. But here is the crucial limitation. You cannot force your die to land on a 6 in order to send that information to someone holding the other die. The outcome of your roll is always random. You only discover the correlation after the fact. This is the heart of the matter. Entanglement is a profound correlation in the quantum properties of particles, like their spin or polarization, a link forged when they interact or are born from a common source. They are described by one single, shared quantum state, a mathematical entity that treats them as an inseparable whole, no matter how far apart they fly. As quantum information pioneer Charles Bennett has explained, entanglement is a resource like energy. It can be used to perform remarkable tasks, but it cannot, by itself, transmit a message faster than light. Einstein's cosmic speed limit remains unbroken. To understand this resource, we need to look at the mathematical description, the wave function. This is not a physical thing, but a set of instructions that encodes all the possible outcomes for the entangled pair. For two entangled photons, their shared wave function might state that their polarizations are perfectly anti-correlated. This means if one is measured and found to be vibrating vertically, the other will instantly, and with 100% certainty, be found vibrating horizontally. But the wave function does not say which photon will be vertical and which horizontal. That specific outcome is born at the random moment of the first measurement. This is why you cannot send a message. You cannot control what you will find. You can only discover the answer that the universe provides in that instant, and in doing so, you instantly define the answer for its partner. It preserves causality because no controlled information travels, yet it completely shatters our classical notion of separate, independent objects. They are two faces of a single quantum coin, and flipping it here defines its state everywhere. This distinction between correlation and communication is everything. It is the key that unlocks how we can actually harness this spooky resource. If we cannot send messages, what incredible tasks can this quantum link actually perform? The spooky link is not just a cosmic oddity, it is a new kind of tool. We have moved from proving its existence to harnessing its power, igniting what scientists call the second quantum revolution. This new era uses the strange rules of quantum mechanics not just to explain the world, but to build things that were once impossible. At the heart of this revolution lies entanglement, the ultimate resource for a suite of technologies that read like science fiction made real. The first and most mature application is in the realm of absolute secrecy, quantum cryptography. Imagine two people, traditionally called Alice and Bob, who need to share a secret message. Instead of relying on complex mathematical codes that a powerful future computer might crack, they use a stream of entangled photons. They each measure their half of the entangled pairs in randomly chosen ways, and through a public conversation about their methods, not their results, they can distill a string of perfectly random numbers known only to them. This is the essence of quantum key distribution. Its security rests on the very principles that once troubled Einstein. If an eavesdropper, Eve, tries to intercept a photon to learn the key, she must measure it. But measuring a quantum system inevitably disturbs it. This disturbance introduces errors that Alice and Bob can easily detect, alerting them to the intrusion. This is rooted in the no-cloning theorem, a fundamental quantum law stating you cannot make a perfect, undetected copy of an unknown quantum state. Eve cannot secretly clone the photon, she can only steal it, and her theft will always leave a trace. The resulting key is then used with unbreakable one-time pad encryption. creating a communication channel whose security is guaranteed by the laws of physics, not just computational difficulty. But the potential goes far beyond secure communication. Entanglement is the essential ingredient that gives quantum computers their awesome and often misunderstood power. While a classical computer bit is either a 0 or a 1, a quantum bit or qubit can be a 0, a 1, or a ghostly blend of both, a superposition. Now link many qubits together with entanglement, and something extraordinary happens. You are not just working with a collection of individual bits. You are working with a single, vast quantum state that can represent a staggering number of possibilities simultaneously. As physicist Michio Kaku has noted, quantum entanglement is the grease that makes quantum computers work. It allows a quantum computer to perform a massive parallel computation on all those possibilities at once. When you finally measure the system, the wave function collapses to a single answer, but the magic lies in choreographing the quantum probabilities so that the correct answer is the most likely one to emerge. This makes them uniquely suited for problems that would take classical computers millennia, like simulating the precise behavior of complex molecules to design new life-saving drugs or materials, or optimizing impossibly large systems like global logistics networks. Other applications are already taking shape. Quantum teleportation uses entanglement combined with a stream of classical information to transfer the exact quantum state of one particle to another distant particle, effectively teleporting its quantum identity without moving the physical particle itself. And quantum sensors employing entangled photons or atoms promise a leap in measurement precision. They could lead to brain scanners that see neural activity with unprecedented clarity, telescopes that peer deeper into the cosmos by overcoming traditional diffraction limits, or navigation systems so sensitive they could detect underground mineral deposits or tiny shifts in gravitational fields. From a philosophical nightmare to a practical toolkit, entanglement has become the silent, spooky engine of a future we are just beginning to build. But if the link is not a signal, what is it? For some, the only way to escape the spookiness is to embrace a reality far more vast and strange. In the late 1950s, a young graduate student named Hugh Everett III proposed a breathtakingly simple, yet infinitely complex alternative. His many worlds interpretation asks us to take the mathematics of quantum mechanics at face value, with no added rules about collapse or observation. In this view, the wave function never collapses. It simply continues to evolve, and every possible outcome encoded within it actually happens. When you measure an entangled particle and get a specific result, the universe does not choose one possibility. It splits like a branching path in an endless cosmic forest. One branch contains you, seeing spin up. Another, nearly identical branch contains a version of you, seeing spin down. Both are equally real. This branching happens at every quantum event, creating a multiverse of staggering proportions. In this framework, entanglement loses its spooky, instantaneous quality. There is no action at a distance because there is no single outcome to coordinate. At the moment the entangled particles were created, the entire universe, including you, the particles, and all possible measurement results became a single, grand, entangled quantum state. As physicist David Deutsch, a prominent advocate, has stated, the multiverse is not a theory in itself. It is a consequence of taking our best theories seriously. When you later perform a measurement, you are not causing a distant particle to snap into place. You are simply becoming aware of which branch of reality you are in. The correlation between the particles was written into the fabric of that branch from the very beginning. So from the perspective of your branch, it looks like a magical connection. But from the bird's eye view of the whole wave function, it is just a static pattern of correlation across a branching tree of realities. This elegantly resolves the EPR paradox without any faster than light influence. The particles are not communicating, Every possible combination of their properties exists in some branch. You find yourself in a branch where the results match, and that feels like a mystery, but it is simply the consistent thread of one story among countless others. It preserves a form of locality and realism, but at an almost unimaginable cost. You trade spooky action for an infinite multiplication of selves and worlds. Is this a more elegant solution? It removes the need for a special, unexplained collapse process. It treats the universe as a single, unified quantum object obeying one smooth equation. But for many, the metaphysical price is too high. It asks us to believe in a reality where every quantum dice roll spawns new universes, where a version of you exists for every fleeting possibility. The interpretation remains just that, an interpretation. It makes the same experimental predictions as the standard view, so science cannot yet choose between them. It becomes a question of philosophical taste. Do you prefer a universe that is single but spooky, or one that is multiplicity but logically seamless? This is not merely abstract speculation. The idea of a branching reality directly informs the work of some quantum computer scientists who see the processing power of their machines as evidence of harnessing calculations across many parallel branches. The journey from Einstein's discomfort has led us here to the edge of a multiverse. Yet, even among these cosmic vistas, a more intimate mystery remains. If reality is so deeply interconnected or endlessly branched, what does that say about us, the observers caught in its web? But this branching, interconnected quantum reality raises a profound and practical question. If particles are truly dancing in superpositions and bound by entanglement, why does the world we touch and see feel so solid, so definite, and so stubbornly local? Why don't we see chairs in two places at once, or feel spooky links to distant objects? The bridge between the bizarre quantum realm and our ordinary experience is built from a process called decoherence. Think of a perfectly still pond, its surface capable of holding intricate, overlapping wave patterns. This is like an isolated quantum system in a pure superposition. Now toss a handful of pebbles into that pond. The clean interference patterns are instantly scrambled into a chaotic mess of ripples. The pebbles represent the environment, and the loss of those clear patterns is decoherence. In essence, decoherence is the process by which a quantum system loses its quantum coherence, its ability to show wave-like interference by becoming entangled with the countless particles in its surroundings. It is not that the superposition vanishes, it is that it leaks out, spreading into the environment in an irreversible way. As physicist Wojciech describes it, decoherence is what makes the classical world emerge from the quantum substrate. The moment a quantum object interacts with even a single photon of light or a stray air molecule, it becomes entangled with that particle. That interaction creates a correlation, a tiny record of the quantum object's state in the environment. But the environment is unimaginably complex, with trillions upon trillions of particles, so that single correlation multiplies instantly into a vast, uncontrollable web of entanglement. The original system's delicate quantum information is not destroyed, but it is scattered into the cosmic noise like a whisper lost in a roaring stadium. For us, trying to observe just the original object, that superposition becomes effectively invisible. The different possibilities no longer interfere with each other in a way we can detect. They simply become alternative histories recorded in the environment. This explains the fate of the most famous quantum thought experiment. Schrödinger's cat is not suspended in a ghostly blend of alive and dead for any measurable instant. The moment the quantum trigger in the box fires, it interacts with the vial of poison, the air in the box, the cat's own atoms. That single quantum event decoheres in a fraction of a nanosecond, branching into an environment containing either a living cat or a cat that has passed, with no observable interference between the two. The universe keeps both possibilities in a sense, but they become dynamically separate, following their own decohered paths. This process is our guardian of classical reality. It protects causality in our everyday world by ensuring that macroscopic objects, which are constantly bombarded by their environment, behave in predictable, local ways. The spooky action of entanglement is always happening, but for large objects, it is happening with everything around them, so rapidly and completely that all the quantum weirdness averages out into the definite world we know. This means entanglement is not rare. It is ubiquitous, the default state of interacting particles. Our classical world of separate objects is the illusion, a stable reality emergent from a deeper, quantum connectedness that is constantly being woven and frayed by decoherence. So if our senses are shielded from this underlying quantum tapestry by decoherence, how can we ever hope to see it or use it? The answer lies in creating a sanctuary, a place where quantum states can be protected from the noisy world long enough to perform their magic. The solid world we perceive may be a magnificent illusion, a hologram projected from a deeper layer of reality. Some of the most radical ideas in modern physics propose that the very fabric of space and time is not the foundation of the universe, but a consequence of something more fundamental, quantum entanglement. Picture empty space not as a blank stage, but as a vast, shimmering network of countless invisible threads, each one an entangled link between quantum bits of information. What we experience as smooth, continuous geometry could emerge from the density and complexity of this underlying web of correlation. This leads to a breathtaking conjecture known as ER equals EPR, proposed by physicists Juan Maldeisner and Leonard Susskind. It suggests a profound duality, a deep equivalence between two of Einstein's ideas that he thought were completely separate. On one side, EPR, the spooky action of entangled particles. On the other, ER, the Einstein-Rosen bridge, a theoretical tunnel through spacetime, what we commonly call a wormhole. The conjecture posits they are not just similar, they are the same thing described in different languages. An entangled pair of particles, according to this view, are not connected by a mysterious force acting across space. They are literally linked by a microscopic wormhole, a bridge in the geometry of spacetime itself. The entanglement is the bridge. This turns our intuition inside out. We usually think of space as the container that allows things to be connected. But here, the connection, the entanglement, is what creates the geometry of space. It is as if the threads of the quantum web, when woven together with immense complexity, stitch the very canvas of reality into existence. This idea finds a natural home in the holographic principle, one of the most profound insights from the study of black holes. The principle suggests that all the information needed to describe a volume of space, like the interior of a black hole or even our entire universe, can be encoded on its lower dimensional boundary, like a two-dimensional screen. Think of a three-dimensional hologram emerging from a flat, two-dimensional surface. In this cosmic hologram, the smooth, warped geometry of spacetime in the interior, the bulk, is built from the intricate quantum entanglement between degrees of freedom on that boundary screen. The amount of entanglement, measured as entanglement entropy, directly relates to the area of surfaces within the spacetime. More entanglement literally weaves more space. A powerful example is the fate of information falling into a black hole. Stephen Hawking showed that black holes evaporate, emitting radiation, but this created a paradox about what happens to the information of what fell in. The holographic view, supported by the ER equals EPR idea, suggests the answer lies in entanglement. The interior of the black hole becomes entangled with the Hawking radiation it emits outside. This entanglement is what geometrically creates the smooth, continuous space inside the black hole. As physicist Leonard Susskind has speculated, the fabric of spacetime itself may function like a quantum error-correcting code, a stable structure built from and protected by these entangled links. If you were to somehow cut all the entanglement threads in a region of space, the geometry would not just empty out, it would cease to exist as a coherent, connected place. Space would dissolve into a disconnected, chaotic quantum foam. This brings us to a stunning historical irony. Einstein spent years rejecting spooky action, believing it violated the logical, geometric universe described by his masterpiece, General Relativity. Yet the latest frontier of theoretical physics hints that his greatest aversion might be the secret ingredient of his greatest achievement. The smooth, dynamic spacetime of general relativity may not be able to exist without the ubiquitous, non-local glue of quantum entanglement. The spooky action he dismissed could be the very thing that stitches his beautiful geometric universe together. Stephen Hawking's greatest discovery became his deepest concern. He showed that black holes are not truly black. Due to quantum effects at their event horizons, they must slowly emit a faint glow of particles, now called Hawking radiation. This radiation carries away energy, causing the black hole to evaporate, shrinking over eons until it vanishes entirely. This elegant idea, however, triggered a crisis that threatened the foundations of physics. According to the classical rules of general relativity, a black hole is defined only by its mass, spin, and charge. Anything else that falls in, whether a star, a book, or a person, is crushed beyond recovery at the singularity. Its information, the unique arrangement of particles that made it what it was, is seemingly erased from the universe. But quantum mechanics has a sacred, non-negotiable rule called unitarity. It states that information can never be truly destroyed, only scrambled and transformed. The universe must keep a perfect ledger. Hawking radiation, as initially understood, appeared to be purely thermal, like the random heat from a stove. It carried no imprint, no fingerprint of the specific matter that formed the black hole. So when the black hole evaporated, that information would be gone forever, violating the quantum rule. This was the black hole information paradox, a clash between the two great pillars of modern physics, and for decades, it seemed one of them had to break. The potential savior in this story is the very phenomenon Einstein rejected. Quantum entanglement offers a way to preserve the cosmic ledger without breaking any rules. To understand how, we need to look more closely at the radiation itself. Hawking radiation is not a simple stream of independent particles. It is born from the quantum vacuum at the event horizon as entangled pairs. One particle falls into the black hole while its entangled partner escapes to infinity. Initially, the escaped particle is entangled with its unfortunate twin inside the black hole. But as the black hole evaporates, it loses mass. The paradox asks what happens to that entanglement when the black hole finally disappears. If the information is lost, the radiation outside would be left in a problematic quantum state. The breakthrough came from applying the tools of quantum information theory to gravity. Physicists like Ahmed Olmary and his collaborators used a powerful concept called the gravitational path integral to calculate the entanglement entropy of the Hawking radiation over the black hole's lifetime. What they found was astonishing. As more and more radiation escapes, a remarkable shift occurs. The radiation particles do not just entangle with the interior. They begin to entangle with each other in an intricate web. After enough time has passed, a new region of spacetime, disconnected from the outside, becomes important in the calculations. This region is called an island. It is not a physical place you could visit. It is a mathematical feature that appears in the equations, and it lies inside the black hole's event horizon. The mathematics shows that the information about what fell into the black hole is not trapped forever at the central singularity. Instead, it is encoded in the complex entanglement patterns of the radiation that has already escaped. The island represents a bridge via entanglement between the distant radiation and the interior. In a profound sense, the information has been teleported out, not by traveling through space, but by being written into the correlations between particles. This resolves the paradox without violating other sacred principles. The no-cloning theorem, which says you cannot copy a quantum state, is safe because the information is not duplicated. It is transferred, it leaves the interior and is reconstructed in the radiation. Locality is also respected because no faster than light signal is sent. The transfer is a global, quantum mechanical reshuffling of entanglement. The interior of the black hole and the faraway radiation become so deeply linked that they are essentially two sides of the same coin. You cannot describe one without the other. This means that from the perspective of someone outside, the information never actually fell into a place of no return. It was always accessible, woven into the fabric of the Hawking glow, if only you had the quantum computer powerful enough to decode its entangled threads. Here, in the most extreme environment the universe can create, we see entanglement's ultimate role. It is not merely a laboratory curiosity or a tool for computation. It appears to be the fundamental mechanism that preserves the consistency of reality itself, ensuring that the quantum story of the cosmos remains coherent from beginning to end. The spooky action that so troubled Einstein may be the silent guardian of cosmic law, the glue that holds the story of the universe together even when gravity tries to tear it apart. The search for entanglement's signature has moved from the emptiness of space to the bustling interior of a living cell. Could the spooky action that stitches together the cosmos also be woven into the very fabric of life itself? This is the provocative question at the heart of quantum biology, a field that asks if evolution has learned to harness the quantum toolkit for survival. It challenges a fundamental assumption that the warm, wet, and chaotic environment inside any organism would destroy delicate quantum states like superposition and entanglement almost instantly through decoherence. Yet, nature has had billions of years to solve problems of exquisite precision, and the evidence suggests it may have found a way to protect quantum effects long enough to gain a critical advantage. Consider the mystery of avian navigation. A bird like the European robin migrates thousands of miles, guided by an internal compass sensitive to the Earth's incredibly weak magnetic field. The leading hypothesis points to a protein in the bird's eye called cryptochrome. When light strikes this molecule, it can create a pair of radicals, molecules with unpaired electrons. These electron spins may become quantum entangled. The Earth's magnetic field could then subtly influence the quantum state of this entangled pair, altering the chemical signals the bird perceives. In this model, the bird is not just sensing a field, it is performing a quantum measurement on an entangled system, using spooky correlations to detect a force far too faint for any classical biological sensor. It is a breathtaking idea that a migrating bird might be a living quantum instrument. Another compelling line of evidence comes from the very foundation of life's energy, photosynthesis. In plants and some bacteria, light-harvesting complexes act as antennae, capturing sunlight and funneling its energy to a reaction center with staggering efficiency, near 100%. Classical physics struggles to explain how this energy finds its optimal path so quickly through a complex molecular network. Experiments suggest the answer may be quantum coherence. The energy does not hop randomly from molecule to molecule. Instead, it exists as a wave of possibility, exploring multiple pathways simultaneously through quantum superposition, a close relative of entanglement, to find the most efficient route. It is as if the plant performs an instantaneous quantum computation to direct its vital energy. This challenges our view of the cell as merely a bag of chemicals. It might be more akin to a carefully tuned quantum environment. The physicist Jim Al-Khalili has suggested that life may have evolved to exploit the quantum world, not as a curiosity, but as a fundamental mechanism. The debates in this field are vibrant and ongoing. Clear, direct proof of sustained entanglement in a living organism remains elusive, as decoherence is a formidable foe. Yet, tantalizing clues keep emerging. Some researchers propose that the sense of smell might involve quantum tunneling, where electrons pass through barriers in odorant receptors, with their probability influenced by the quantum vibrational states of the scent molecule. This could explain our ability to distinguish between molecules that are chemically identical but shaped like mirror images of each other. Even enzyme catalysis, the process that speeds up vital biochemical reactions, might be enhanced by quantum effects that help particles tunnel to where they need to be. If these hypotheses are confirmed, the implications are profound. It would mean the boundary between the quantum and classical worlds is not a sharp line, but a blurred frontier where life has learned to dance. The spooky action would not be confined to labs and stars. It would be a silent partner in the scent of a flower, the green of a leaf, and the incredible journey of a bird across a continent. This realization forces a new question. If nature can build bridges between the quantum and the living, can we learn to do the same, not just in sterile machines, but in technologies that heal, sense, and interact with the biological world? Our exploration has led us from the living cell to the edge of a profound and personal question. If the universe is woven from these instantaneous, non-local threads, what does that say about the nature of our own choices? The spooky action of entanglement does not just challenge physics, it forces a re-examination of deep philosophical pillars, free will and determinism. At its core, this is a debate about the source of randomness. When we measure an entangled particle and get a random result, is that randomness truly fundamental, a genuine creation of something new in the universe? Or is it merely a reflection of our ignorance, like not knowing which card is on top of a shuffled deck that was arranged all along? One provocative answer comes from the free will theorem, proposed by mathematicians John Conway and Simon Kochen. They start with a few simple assumptions: the laws of quantum mechanics, the special theory of relativity, and crucially, the idea that experimenters possess free will to choose how they set their measuring devices. From these foundations, they use a thought experiment involving entangled particles to argue that if we have that freedom, then the particles themselves must also possess a form of free will. Their theorem suggests the randomness in a quantum measurement is not a hidden trick. It is a genuine, irreducible choice made by the particle at the moment it is observed. This is a staggering inversion. We often think of our free will as emerging from the complexity of our brains, but Conway and Kochen imply it might be a fundamental feature of reality, built right into the fabric of matter at the smallest scales. Our human sense of agency could be a reflection of a deeper, quantum level of spontaneity. It is a view that gives the universe an open future where genuine novelty is possible. Yet there exists a starkly different interpretation, one that preserves a clockwork cosmos by making a radical sacrifice. It is called superdeterminism. In this view, proposed by physicists like Nobel laureate Gerard T. Hooft, there are no loose threads, no free choices, not even for us. Everything in the universe, from the motion of galaxies to the firing of a neuron in a scientist's brain, is the inevitable outcome of conditions set at the dawn of time. All events are pre-written in a single, unbreakable chain of cause and effect. This includes the seemingly random choice of which measurement to perform in a Bell test experiment. If superdeterminism is true, then the cosmic Bell tests we discussed earlier, which used ancient Starlight as a random number generator, were never truly free. The photons from that distant star and the decision of the scientist to use them were destined to align in just the right way to produce the illusion of quantum randomness and non-locality. From this perspective, Bell's theorem does not prove spooky action. It merely reveals that our measurement settings were never independent of the particles they were measuring. They were secretly correlated from the beginning of the universe, preserving a local, hidden variable reality. It is a logically consistent escape hatch, but one that comes at a great cost. It suggests our deepest feelings of deliberation and choice are a compelling illusion, a story we tell ourselves as we act out a script written at the Big Bang. So we are left with two profound and competing visions, both forced upon us by the same quantum evidence. Does entanglement reveal a universe that is deeply interconnected and open, where causality is looser and genuine novelty emerges at every level? Or does it point to a universe that is utterly predetermined, where our struggle to understand it was itself determined eons ago? This is not merely academic, it shapes how we see our place in the cosmos. Are we active participants in a story still being written, or are we passive readers of a book whose final page was printed long ago? The mystery of entanglement holds up a mirror, and in it we see not just particles, but the puzzle of our own existence reflected back at us. The very act of looking seems to hold a strange power in the quantum realm. At the heart of the spooky action lies a question so fundamental it remains unanswered: the quantum measurement problem. What exactly happens in that instant when a haze of possibilities becomes a single, definite fact? When you measure one particle of an entangled pair, its partner's fate is sealed instantly across any distance. But where and how does this collapse of possibilities actually occur? Think of Schrödinger's famous cat suspended in that ghostly blend of states. The moment of truth comes when the box is opened, but what qualifies as opening the box? Is it the Geiger counter clicking, a pointer moving on a dial, a computer logging a 1 or a 0, or the conscious awareness of a scientist seeing the result? This is not a trivial puzzle. It cuts to the core of what we mean by reality itself. Is the wave function, that mathematical description of all possibilities, a real physical thing that undergoes a sudden physical change? Or is it merely a catalogue of our knowledge, updating abruptly when we learn something new, like finding a card you knew was in the deck? Different interpretations of quantum mechanics offer wildly different answers, and your choice shapes how you see the entire universe. The traditional Copenhagen interpretation, championed by Niels Bohr, posits that the act of measurement by a classical apparatus causes the collapse. It draws a fuzzy but necessary line between the quantum world and the classical world of our instruments. Yet it remains silent on where that line actually is, or what magic a large, classical object possesses that a small quantum one does not. In stark contrast, the many worlds interpretation removes the problem entirely by declaring that collapse never happens. Every possible outcome simply occurs in a newly branched reality. There is no single moment of definition, only a perpetual splitting of the cosmic story. But a third class of ideas, objective collapse theories, proposes a more physical solution. Models like GRW, named for their creators Garodi, Rimini, and Weber, suggest that wave functions are inherently unstable. They spontaneously and randomly collapse on their own, with the probability of collapse increasing with the size and complexity of the system. A single electron might stay in a superposition for a long time, but a large object like a cat or a detector would collapse almost instantly. This would explain why we never see macroscopic objects in two places at once, not because we look at them, but because they cannot sustain such states. Even more intriguing is the suggestion by physicist Roger Penrose that the culprit behind collapse might be gravity. He proposes that a particle in superposition creates a subtle ambiguity in the fabric of spacetime itself. The universe, seeking a single, consistent geometry, forces a collapse after a certain time. This tantalizing idea directly links the two great pillars of physics, quantum mechanics and general relativity, through the very act of measurement. In our laboratories, this ambiguity is palpable. In an entanglement experiment, when does the correlation become a definite record? Is it when the photon strikes the detector's sensor, when that electrical signal is amplified, when it is stored as a bit in a computer's memory, or only when a human mind finally comprehends the printout? The chain is long, and at no point is there a clear, agreed-upon threshold where quantum possibility becomes classical fact. Entanglement magnifies this uncertainty because the collapse, wherever it happens, is not local. It defines the state of the entire entangled system, everywhere at once. This foundational gap in our understanding means we have mastered the mathematics of prediction without grasping the mechanism of manifestation. We can calculate probabilities with breathtaking accuracy, yet we cannot say what physically transpires in the moment a probability turns into a history. Until we solve the measurement problem, the spooky action will retain a layer of profound mystery, a reminder that our grasp of reality is still, in many ways, a story waiting for its final chapter. But to build a global network, we face a fundamental quantum limitation. Entangled particles are delicate, and sending them through hundreds of kilometers of optical fiber causes them to be lost or scattered, severing the precious link. To create a truly quantum internet, we need a way to generate entanglement between particles that have never even met across vast distances. The solution is a mind-bending protocol called entanglement swapping. Picture 4 individual photons labeled A, B, C, and D. Photons A and B are an entangled pair created together in one lab. Photons C and D are another entangled pair created in a separate lab, perhaps in a different city. These two pairs share no history, no connection. Now we take photons B and C and bring them together at a central station. We don't look at them individually. Instead, we perform a special joint measurement on them, known as a Bell state measurement. This measurement does not tell us anything about B or C's own states. Instead, it asks a single, profound question about the relationship between B and C. In the instant we get an answer, something magical happens. Photons A and D, the partners that were never in the same place and never interacted, are suddenly projected into a perfect entangled state. The act of measuring B and C together has teleported their entanglement onto A and D. It is as if the invisible thread connecting A to B and the thread connecting C to D have been spliced together, creating a new, direct thread between A and D. The original links are severed, but a new, longer connection is born. This is the cornerstone of a quantum repeater, a device that will one day act like a quantum relay station. Instead of trying to send a fragile, entangled photon all the way from New York to London, you would create a chain of shorter, more reliable links between intermediate nodes. At each node, entanglement swapping stitches these short links together into one continuous, long-distance connection. As quantum pioneer Anton Zeilinger demonstrated, this process is essentially the teleportation of entanglement itself. The protocol cleverly respects all the quantum rules. The Bell measurement at the central station produces a random outcome, and to complete the entanglement between A and D, that classical result must be sent to the stations holding A and D via ordinary, slower-than-light communication. They then perform a simple correction on their photons based on that message. This final classical step ensures no information travels faster than light, preserving causality, while the quantum correlation appears instantly across the newly forged link. The implications are staggering. Imagine a future where quantum computers in different cities are not isolated marvels, but nodes on a quantum cloud. Through a network of entanglement swapping, they could share quantum information and processing power, tackling problems no single machine could handle. Ultra-secure cryptographic keys could be distributed across continents, creating a new global standard for privacy. Research consortia like the Quantum Internet Alliance are already building prototype networks in Europe and beyond. turning this theoretical wizardry into tomorrow's infrastructure. This is the ultimate engineering of spooky action, taking a phenomenon that once baffled Einstein and weaving it into the backbone of a new technological era. The power of entanglement comes with a profound vulnerability. This invisible thread connecting particles is astonishingly fragile, easily severed by the slightest whisper from the chaotic world around it. For all its potential, the spooky action melts away under the warmth of reality, a phenomenon physicists call decoherence. This is the central, daunting challenge for every quantum technology. Imagine trying to preserve a perfect snowflake in your hand. Your body heat alone is enough to transform its intricate crystal structure into a drop of water. In the quantum realm, that heat is everywhere in the form of thermal vibrations, stray electromagnetic fields, and even the minuscule imperfections in the materials we build with. These environmental noises constantly jostle and interact with our delicate qubits, scrambling their precious superpositions and erasing the entanglement between them. As MIT professor Isaac Chuang has pointed out, the enemy of quantum computing is decoherence, and this battle extends to every application that relies on the quantum link. To win this war, scientists must create sanctuaries of near-perfect stillness. This often means plunging systems to temperatures within a fraction of a degree above absolute zero, colder than the void of deep space, to freeze out thermal noise. It means constructing elaborate vacuum chambers to trap individual atoms or ions, isolating them from collisions with air molecules. For superconducting qubits, the heart of many quantum computers, it requires exquisitely engineered chips shielded in multiple layers of metal to block even the faintest stray radio waves. Consider the quest for a quantum memory, a device that can store an entangled state like a computer stores a bit. One promising approach uses rare earth ions embedded in ultra-pure crystals, their quantum states protected by the crystal's lattice. But the efficiency of writing in and reading out the entanglement and the speed at which it can be done remain significant hurdles. The grand challenge, however, is scaling. A handful of entangled qubits in a lab is a scientific triumph, but a useful quantum computer capable of solving real-world problems may require millions of entangled qubits working in concert. Maintaining the coherence and connections across such an immense quantum system is an engineering marathon of almost unimaginable difficulty. It demands not just better isolation, but revolutionary advances in control systems and, crucially, quantum error correction. This is a field where information is not stored in a single, fragile qubit, but spread out across many in an entangled web, creating a logical qubit that is far more robust. Building such a fault-tolerant system is the essential next step. These limits are not a condemnation of the technology, but a map of the frontier. They keep our expectations grounded in the monumental difficulty of the task, which in turn makes the progress being made all the more extraordinary. Every second added to a qubit's coherence time, every new method to generate entanglement with higher fidelity, is a hard-won victory in the fight against noise. The strange physics of entanglement has long since escaped the laboratory, seeping into the stories we tell and the art we create. It offers a powerful new language for the oldest human mysteries, the invisible threads that bind us. When a novelist writes of characters who sense each other's pain across continents, or a filmmaker depicts love as a force that bends time, they are channeling the essence of spooky action, using quantum non-locality as a metaphor for the deepest human bonds. Richard Powers' novel The Overstory presents a forest not as a collection of individual trees, but as a vast communicative network, a hidden web of relation where distress signals and nutrients are shared in ways that defy simple, local cause and effect. This vision of a connected, whispering world resonates profoundly with the quantum view of a universe woven from correlation. Similarly, in Christopher Nolan's film Interstellar, the emotional connection between characters is presented not as mere sentiment, but as a tangible, trans-dimensional force, a bridge across space-time that guides and saves. It is a poetic leap, translating the cold mathematics of entanglement into the warm language of the heart. As physicist and novelist Alan Lightman observes, science and art are two different ways of looking at the world, but they both seek the same thing, truth. One seeks truth in external reality, the other in internal, human reality. Entanglement provides a rare conceptual bridge between these realms. This cultural absorption is visible everywhere once you know to look. Poets speak of lovers as entangled particles, their fates decided by a single, shared measurement. Visual artists create installations with mirrors and light that explore non-locality, where a change in one part of the room instantly alters the experience in another. Composers have even used quantum algorithms, the very mathematics of superposition, to generate sequences of notes, creating music born from the core of uncertainty. The phrase spooky action itself has entered our common lexicon, often deployed to describe those eerie coincidences, the sudden phone call from the person you were just thinking about, the sense of a connection that operates outside of ordinary time. These are not scientific claims but cultural echoes. They show how a baffling physical phenomenon satisfies a deep, pre-existing human intuition that we are part of something larger, that separation might be an illusion our senses have constructed. Art does not explain entanglement, but it allows us to feel its implications, to sit with the wonder and the unease of a universe that is fundamentally relational. When a song moves us or a story makes us feel seen, we are, in a way, experiencing a classical shadow of that quantum wholeness, a reminder that some connections simply are, defying all distance and logic. The most profound ideas can be made tangible with simple tools. To bring the mystery of entanglement out of theoretical papers and into the light of understanding, educators have crafted ingenious demonstrations that require no supercooled magnets or vacuum chambers, just a bit of creativity and a deck of cards. In classrooms around the world, students are now encountering the core principles of quantum mechanics through hands-on games that reveal the strange logic of our universe. The goal is not to replicate the physics, which would be impossible with classical objects, but to illuminate the conceptual heart of the matter, the breakdown of local realism. A powerful and popular exercise is the CHSH game, named for the physicists who refined Bell's theorem. It frames the violation of a Bell inequality as a cooperative challenge. Two students playing the roles of separated particles are each given a random question. Without communicating, they must each provide an answer. If they were classical objects operating with pre-agreed upon strategies, their ability to win, to produce correlated answers that satisfy a specific rule, is capped. They can only succeed a certain percentage of the time, but if they were somehow quantum entangled, their theoretical success rate would be higher. Playing this game repeatedly makes the statistical limit visceral. Students feel the frustration of the classical ceiling, and in that moment, they understand what it means for quantum correlations to smash through it. It transforms an abstract inequality into a shared experience of limitation and potential. Another beautifully direct demonstration uses nothing more than polarizing filters and a light source, often a simple laser pointer. Light polarization is a perfect, accessible analog for a quantum property like spin. By sending light through a pair of filters, educators can show how the orientation of one filter instantly determines whether light will pass through the second, a clear model of correlation. Introducing a calcite crystal which splits a single light beam into two polarized paths can simulate the creation of an entangled pair. The key lesson, as quantum education advocate Joe Diamond emphasizes, is that if you cannot explain it simply, you have not understood it well enough. These demonstrations drill home the crucial distinction. When students see that changing the first filter after the light has passed through does nothing to the already determined outcome at the second filter, they grasp that this is not a signal. The correlation was locked in at the source the moment the light was created or split. The fate was shared from the beginning. This demystifies the spookiness, replacing magic with a new, more robust intuition about probability and connection. By using colored dice to represent hidden variables or specially prepared card decks where every pair is mysteriously matched, these activities make the philosophical debate between Einstein and Bohr something you can hold in your hand. They plant a seed of quantum literacy, showing that this is not an untouchable mystery for a select few, but a describable feature of reality that anyone can begin to explore. When a student successfully predicts the outcome of a CHSH game or watches a polarized beam of light, they are not just learning physics. They are training their mind to see the world not as a collection of isolated things, but as a web of deep, pre-established correlations. This early engagement builds a bridge, inviting the next generation not to be passive observers of a technological revolution, but active participants and informed shapers of the quantum age ahead. The magic of entanglement is written in a language of pure geometry and probability. To move beyond metaphor and grasp its true nature, we must step into the abstract world where quantum mechanics lives, the realm of Hilbert space. Think of this not as a physical place, but as a vast, multidimensional stage where every possible state of a quantum system is a point or a vector. A single particle's condition, its superposition of possibilities, is a single arrow pointing in a certain direction within its own private Hilbert space. The profound shift happens when we bring two particles together. Their combined state does not live in two separate stages side by side. According to the rules laid down by pioneers like John von Neumann, the stage for the pair is built by merging their individual spaces through a mathematical operation called the tensor product. This creates a new, larger arena where every possible combination of the particle states has its own unique corner. Here is where entanglement reveals its mathematical heart. In this combined space, most states are separable. This means you can point to a specific state for particle A and a specific state for particle B, and their combination describes the whole system. It is like having two independent arrows, but a special, exotic class of states defies this simple breakdown. These are the entangled states. In them, you cannot pin down a definite state for particle A alone or particle B alone. The system is described only as a whole. Mathematically, its state vector cannot be factored into a single product of two individual vectors. It is non-separable. This is not a philosophical statement. It is a precise, calculable feature of the vector in that abstract space. We can make this concrete with the simplest quantum system, a qubit. Imagine a qubit as an arrow that can point up, representing a 0, or down, representing a 1, or any probabilistic blend in between. Now take two qubits. A separable state might be qubit A definitely up and qubit B definitely down. We can write that cleanly as a product, but consider the most famous entangled state, the Bell state. Its mathematical description is the superposition of both qubits up plus both qubits down, all divided by the square root of 2. Written in the bracket notation von Neumann helped popularize, it is the state 0, 0 plus 1, 1 over root 2. Look at it closely. You cannot isolate a term that says only what qubit A is doing. The plus sign inextricably links their fates. If you try to describe qubit A by itself from this state, the mathematics forces you into a description of complete randomness, a 50-50 probability of up or down. Its definite property only emerges in relation to its partner. This formalism makes the spooky action clear and inevitable. A measurement is mathematically represented by a projection operator. When you measure qubit A in the Bell state, you force it to choose up or down. The act of projection instantly picks out one term of the superposition. If you get up, the entire shared state collapses, not just for qubit A, but for the combined system. the plus sign vanishes and qubit B is now definitively up as well. The tensor product structure shows why this influence is instantaneous and why you cannot use it to send a message. Any local operation you perform on just qubit A, any rotation or manipulation within its own small space, can only affect the separable parts of the state. It cannot create the non-separable plus sign that is the essence of the link. Entanglement is a resource precisely because it is fragile and non-local in this geometric sense. The mathematics even gives us a ruler to measure the strength of this ghostly bond through the Schmidt decomposition and the concept of entanglement entropy. This is a number that quantifies how much the state of the whole system resists being described as the state of its parts. For a separable state, the entanglement entropy is 0. For a maximally entangled Bell state, it is at its maximum. Every experiment that confirms the violation of Bell's inequality is a direct test of these equations. The correlations that seemed so spooky are exactly what the tensor product and the projection of non-separable vectors predict. So while the Hilbert space may be an abstract landscape, its geometry is the real scaffolding of our world. The spooky action is not a bug in reality, but a feature written into its deepest mathematical code. The abstract mathematics of Hilbert space finds its most dramatic expression not in isolated particles, but in the collective dance of billions within a solid piece of matter. Here, in the field of condensed matter physics, entanglement reveals itself as the architect of entirely new phases of existence, materials with properties that defy classical intuition. We are entering the realm of topological order, where the quantum link becomes a global, organizing force. Imagine an ocean where the water is perfectly still and insulating in its depths, yet its surface churns with a persistent, frictionless current. This is the essence of a topological insulator. The electrons within are not acting as independent particles. They are part of a vast, entangled quantum wave, a choreography that forces electricity to flow without resistance along the material's edges, while the interior remains an insulator. The robustness of this surface conduction is the miracle. You can scratch the material, introduce impurities, or deform it slightly, and the edge current persists. It is protected not by the perfection of the material's chemistry, but by the global topological pattern of entanglement woven through the entire electron sea. As Nobel laureate Frank Wilczek notes, these are states of matter that remember their history. Their properties are encoded in the shape of their quantum wave function, a shape that cannot be smoothly deformed away by local disturbances. This is long-range entanglement made tangible, a collective phenomenon where the fates of countless particles are so deeply interlinked that the system develops a memory and a resilience of its own. A prime example of this organizational power is the fractional quantum Hall effect. When a two-dimensional sheet of electrons is subjected to an intense magnetic field at very low temperatures, something extraordinary happens. The individual electrons vanish, in a sense, into a new, emergent entity. They form a highly entangled quantum liquid, and from this collective state, new particles emerge. These are not electrons or protons, but quasi-particles that carry a fraction of an electron's charge. Their behavior is governed by exotic rules called anyonic statistics, a middle ground between the familiar statistics of bosons and fermions. The key for quantum technology is that the quantum information stored in a pair of these anyons is not stored locally on either one. It is stored in the topological braiding of their world lines, in the history of how they have been moved around one another in the entangled background. This makes the information incredibly resilient to local noise, a property that could form the basis for a fault-tolerant topological quantum computer. This vision drives research efforts like Microsoft's Station Q, which focuses on engineering materials that host Majorana zero modes, another type of quasi-particle predicted to arise from non-local entanglement in superconducting systems. These modes are theorized to be their own antiparticles and to encode quantum information in a similarly non-local way, making them ideal candidates for stable qubits. What we are witnessing is a profound shift in perspective. Entanglement is no longer just a curious link between two photons in a lab. It is a fundamental organizational principle of nature, capable of giving rise to entirely new forms of matter with revolutionary properties. From perfect conductors to exotic quasi-particles, the spooky action has scaled up, becoming the hidden blueprint for materials that could power the next technological age and reveal deeper truths about the quantum world itself. The act of looking does more than just reveal a quantum state. It can actively hold it in place. This is the quantum Zeno effect, a phenomenon where constant observation acts like a cage, preventing a system from evolving naturally. It takes the old saying about a watched pot never boiling and finds a startling truth in the mathematics of the quantum world. The core idea is rooted in the wave function's behavior upon measurement. When you measure a quantum system, you force it to choose a definite state from its cloud of possibilities, a process called the collapse of the wave function. Immediately after this collapse, the system begins to evolve again, its wave function spreading out into new superpositions. But if you measure it again very quickly, you collapse it once more, likely back to that same starting point. With each rapid-fire measurement, you reset the evolutionary clock. It is like trying to leave a room, but someone keeps opening the door to check if you are still there, interrupting your journey every time you take a step. As physicist Baidyanath Misra observed, a system under continuous observation has no time to evolve. For an unstable particle that would normally decay, this relentless scrutiny can effectively freeze it in its initial, undecayed state. Experiments have made this abstract principle tangible. In labs using trapped ions or superconducting qubits, researchers apply a series of quick, gentle measurements. They watch as the qubit, which would ordinarily flip into a different state due to its environment, remains stubbornly locked in place, held by the rhythm of observation. The implications for entangled systems are profound. Decoherence, the process where entanglement unravels due to environmental noise, is a form of evolution. The entangled state wants to drift apart to become separable, but the quantum Zeno effect offers a potential defense. By frequently checking whether an entangled pair is still in its desired, linked state, each measurement can project it back onto that fragile connection, prolonging its useful lifetime. This is not just watching, it is actively shepherding. It is a potential tool for building more robust quantum memories, where the very act of monitoring becomes a form of preservation. Yet this effect adds another layer of mystery to the measurement problem we encountered earlier. It blurs the line between observer and observed in the most active way possible, showing that our interventions do not just reveal reality, they can sculpt its very dynamics. The spooky action of entanglement, it seems, can be sustained by a watchful eye, forcing us to ask, what does it truly mean to observe, and when does protection become control? The quantum world and the cosmic stage of gravity remain stubbornly separate in our theories, a divide that has challenged physicists for a century. To bridge this gap, researchers are now turning to the very phenomenon that defines the quantum realm, using entanglement as a probe to question gravity itself. The ultimate goal is a theory of quantum gravity, a unified description of reality where the force that bends starlight and the spooky action that links particles are two faces of the same cosmic coin. At the heart of this quest is a deceptively simple experiment that has never been done. Can two objects become entangled through their mutual gravitational attraction alone? Imagine two tiny, mirrored spheres, each smaller than a grain of sand, suspended in a perfect vacuum and cooled to near absolute zero. If you bring them close together, their minuscule gravitational pull on each other should, according to some theories, create a quantum link. If scientists can measure this, it would prove that gravity is not just a classical force described by Einstein's geometry, but a fundamentally quantum player capable of generating entanglement. As physicist Vlatko Vedral has noted, the next big step is to see entanglement in systems where gravity is important. This is not about astronomy, but about tabletop experiments that listen for the quietest whisper in the universe, the quantum hum of mass itself. Other proposals are even more ambitious. Could future upgrades to gravitational wave observatories like LIGO detect a signature of quantum entanglement in the cosmic events they witness? When two black holes collide, their final moments are a storm of quantum gravity. Some models suggest the gravitational waves they emit might carry subtle correlations, a faint echo of the entanglement that once bound the holes together. Detecting this would be like hearing the quantum structure of spacetime ring like a bell. On the theoretical front, entanglement is already reshaping how we model the cosmos. The holographic principle and ideas like the AD/CFT correspondence suggest that the geometry of spacetime, its curves and warps, emerges from a dense web of quantum entanglement on a lower dimensional boundary. In this view, a wormhole is not a tunnel through space, it is a manifestation of maximum entanglement. Researchers use mathematical structures called tensor networks to literally build up models of space from these entangled links, showing how connectivity creates geometry. This turns the quest on its head. We are no longer just asking if gravity can create entanglement. We are asking if entanglement, the spooky action, is what creates gravity and the stage of space and time in the first place. It suggests that the cosmos we inhabit may be a magnificent, dynamic tapestry woven from countless threads of quantum connection. Solving this puzzle would not only complete Einstein's dream of a unified theory, it would reveal that the strangest feature of the small-scale world is, in fact, the hidden architect of the largest scales of all. This immense power carries a profound responsibility. The same quantum entanglement that could heal diseases and connect continents also holds the potential to destabilize the very foundations of our global society. The technologies born from spooky action are inherently dual use, meaning their benefits are shadowed by significant risks. A quantum computer capable of simulating new life-saving drugs could, with the same processing power, crack the cryptographic codes that protect every online transaction, state secret, and private communication in the world today. This is not a distant science fiction scenario. Security agencies and corporations are already racing to harvest encrypted data now, with a plan to store it until a sufficiently powerful quantum machine exists to decrypt it years later. The moment that machine comes online, it could trigger a silent crisis, rendering much of our digital world's privacy instantly and irrevocably transparent. As philosopher Shannon Valor has cautioned, we need an ethical framework for quantum technologies before they reshape society. This urgent call to action highlights that our scientific leap must be matched by an equally ambitious leap in foresight and governance. The question is no longer just if we can build these tools, but who will control them and for what purpose. Consider the development of ultra-sensitive quantum sensors. These devices promise to detect the earliest tremors of an earthquake, saving countless lives by providing precious minutes of warning. Yet, the identical technology could map underground bunkers with unprecedented clarity, or track the silent movements of submarines across ocean depths, fueling a new era of surveillance and geopolitical tension. This duality forces us to confront a potential quantum divide, where access to these transformative tools becomes concentrated in the hands of a few powerful nations or corporations, exacerbating existing global inequalities. A world where only some possess quantum-secured communications and quantum-enhanced economies would be a world of deepened instability. The response to this challenge is already taking shape in the urgent global effort to develop and deploy quantum-safe cryptography. This involves creating new encryption algorithms based on mathematical problems even a quantum computer would struggle to solve, that can be integrated into our existing digital infrastructure. It is a monumental task of global software and hardware updates, a race against the clock to build new locks before the old keys are forged. Furthermore, the vision of a quantum internet introduces its own complex web of ethical dilemmas. Who will have access to this ultra-secure network? How do we prevent it from becoming a tool for exclusive control or intrusive monitoring? These questions point to the need for entirely new concepts, like quantum digital rights and international treaties governing the use of quantum capabilities in conflict. Engaging with these considerations now is not a distraction from progress. It is an essential part of the journey. It ensures that the incredible power unlocked by understanding entanglement is guided not merely by technical prowess, but by a shared wisdom and a steadfast commitment to the common good. The story of spooky action thus becomes a mirror, reflecting back our own choices about the future we wish to build. The mathematics of entanglement suggests a universe built not from isolated points, but from relationships. This scientific truth echoes a human experience far older than quantum theory. We feel the invisible threads of connection in a mother's instinctive knowledge of her child's distress across a city, or in the shared grief that sweeps through a community with the news of a loss. While not a literal quantum link, this deep empathy mirrors, in a poetic and profound way, the non-local correlations of physics. It reminds us that our classical world of separate bodies and distinct lives might be a surface reality, beneath which runs a current of fundamental togetherness. The spiritual teacher Thich Nhat Hanh expressed this beautifully, noting we are here to awaken from the illusion of our separateness. The discovery of entanglement does not validate mysticism, but it powerfully expands our philosophical vocabulary. It challenges the atomistic view that we are merely independent entities bumping around in a void. Instead, it offers a model where existence itself might be relational. Your identity is not a solitary fact, but emerges from your connections, your history, and your interactions with everything around you. This perspective resonates far beyond the lab. Look at a forest where trees share nutrients and warnings through vast fungal networks, an ecological web of mutual support. Observe the global economy, where a decision in one nation ripples through markets worldwide. Watch a social movement ignite across continents, fueled by a shared idea. These systems all demonstrate that connection is a fundamental, organizing principle across every scale of reality, from the quantum to the cosmic to the human. Embracing this view carries a quiet responsibility. If particles defying vast distances are part of a single whole, then perhaps our human divisions, our conflicts and isolations, are constructs we have built upon a deeper unity. This is not a call to abandon science for spirituality, but an invitation to let science inspire a wider wisdom. The spooky action teaches us that to understand anything, we must understand its relationships. Applying that insight to our lives, our communities, and our planet might be the most important entanglement of all. The line between profound science and compelling fantasy can be surprisingly thin. With a phenomenon as strange as quantum entanglement, it is essential to separate the rigorously verified from the wishfully imagined. A persistent myth, fueled by the phrase instantaneous correlation, is that entangled particles could form a faster-than-light telephone, allowing us to send messages across galaxies or even backward in time. The truth, while no less astonishing, firmly preserves the structure of our universe. You cannot dictate the random outcome of your measurement to encode a message for someone holding the other particle. You only discover what the universe provides, and only afterward by comparing notes over a classical channel. Can you both see the spooky correlation? This is the safeguard of the no communication theorem, a mathematical proof that entanglement alone cannot transmit information. Causality, the rule that cause must precede effect, remains unbroken. You cannot warn a past version of yourself or signal a distant starship in real time. Another popular idea suggests that human consciousness, through focused thought, can directly influence or collapse quantum systems in a significant, controllable way. This notion often appears in discussions linking spirituality to quantum physics, while the role of the observer in measurement is a genuine and deep mystery in quantum foundations. Leaping from that to the idea that our thoughts can reliably alter macroscopic reality lacks any support from rigorous experiment. The environment, through decoherence, is overwhelmingly powerful in determining outcomes for large-scale systems. As physicist Sean Carroll wisely notes, quantum mechanics is weird, but it is not magic. Its rules are strict and mathematically precise. These rules also set clear boundaries on what entanglement cannot accomplish. You cannot use it to build a perpetual motion machine that creates energy from nothing. You cannot exploit spooky correlations to predict the stock market with certainty, as the outcomes remain fundamentally probabilistic. And you cannot forge supernatural psychic links between people, as our brains are vast, warm, classical systems shielded from sustaining the delicate quantum states needed for such a connection. To harness entanglement, we must work within its framework, which requires prior interaction to create the link, or sophisticated protocols like entanglement swapping that still rely on slower-than-light communication to complete the process. By understanding these limits, we do not diminish the wonder of entanglement. We actually deepen our appreciation for it. Grounding the phenomenon in established physics protects it from becoming a vague metaphor for anything mysterious and allows its true, revolutionary potential to shine. The real magic lies not in breaking the universe's rules, but in learning to use its most subtle and profound rules to build a better future. This clarity invites a final, reflective look at the journey we have taken, from a thought experiment in a quiet study to a force reshaping our world. The equations that describe entanglement possess a stark and minimalist beauty. On a graph plotting the results of a Bell test, a smooth curve of data points arcs gracefully, then crosses a bold, straight line representing the absolute limit of any local, realistic universe. That single, defiant crossing is more than a statistical victory. It is a visual poem, a silent testament to a truth that defies common sense. Within a quantum computer's chilled heart, the choreography is invisible but no less elegant, as qubits in superposition perform a ballet of probabilities, their entangled states shifting in a complex harmony that follows mathematical scores of exquisite precision. Scientists who work in this realm frequently reach for the language of art to describe their discoveries. They speak of a theory's elegance, a proof's beauty, or an experiment's deep satisfaction. The great physicist Paul Dirac once asserted that it is more important to have beauty in one's equations than to have them fit experiment, a statement that reveals a profound faith in the universe's inherent harmony. This pursuit is not merely technical, it is an aesthetic drive, a search for patterns that feel right, symmetrical, and true. The strange non-locality of entanglement, this idea that separate things are fundamentally linked, resonates with artistic and philosophical visions of wholeness that have echoed through human culture for millennia. It finds a mirror in the interconnected brushstrokes of a pointillist painting, where individual dots merge into a unified scene, or in the woven threads of a tapestry, where a single strand gains meaning only from its relationship to all the others. Even the term spooky action at a distance, born from Einstein's skepticism, has taken on a poetic life of its own, capturing the thrilling unease of the unknown with a phrase that feels more like the title of a mystery novel than a laboratory observation. This aesthetic dimension invites everyone in, not just the specialists, You do not need to solve the Schrödinger equation to feel a sense of awe when you learn that two particles can share a single fate across the void of space. That awe is the starting point of all science and all art. It is the human response to a universe that is far stranger, more interconnected, and more beautifully ordered than we ever could have imagined. Our journey to comprehend entanglement, then, is not a cold dissection of facts. It is a deeply human story of curiosity reaching for wonder, of logic embracing mystery, and of finding, in the mathematics of the very small, a surprising and enduring kind of grace. These abstract ideas become visceral when you step into the role of the observer yourself. To truly grasp the weight of quantum strangeness, we must move beyond equations and engage our own intuition with a few challenging thought experiments. The first is a stark variation on Schrödinger's famous cat, often called the quantum suicide experiment. Imagine a person in a sealed room with a device that will activate based on the random decay of a single radioactive atom. If the atom decays, the device ends the person's life. If it does not decay, the person lives. Now, from the perspective of the many worlds interpretation, every second the universe branches. In one branch, the atom decays. In another, it does not. The person, as a conscious observer, only continues to have experiences in the branches where they survive. From their subjective point of view, they would witness the device failing to activate again and again, no matter how unlikely survival becomes in any single branch. They would experience a bizarre form of subjective immortality, always finding themselves in the timeline where the quantum dice roll in their favor. The purpose here is not to dwell on the grim mechanism, but to feel the conceptual shift. It forces you to confront probability not as a prediction of a single future, but as a measure of your presence across a branching multiverse. Your intuition about a single, shared reality begins to fray at the edges. This leads directly to an even more profound puzzle about perspective itself, known as Wigner's friend. Conceived by Nobel laureate Eugene Wigner, it begins simply. His friend goes into a sealed lab and performs a measurement on a quantum system, say, determining the spin of an electron. From the friend's perspective inside the lab, the measurement happens, the wave function collapses, and the electron has a definite result. The friend writes it down. But Wigner is outside the lab door. He has not yet looked inside. According to the standard quantum rules, Wigner must describe the entire lab, including his friend and the electron, as one giant, entangled quantum system still in a superposition of all possible outcomes. For Wigner, the wave function has not collapsed, so we arrive at a paradox. Was the wave function collapsed when his friend looked, or only when Wigner learned the result? Which description is the real one? Wigner himself pondered this deeply, questioning where the boundary of reality truly lies. Now extend this with entanglement. Imagine Wigner's friend measures one particle of an entangled pair inside the lab. The friend now knows the state of both particles instantly, but Wigner, light years away with the other particle, still describes the entire cosmos spanning system, including his friend's lab, as being in a blurred superposition. Does his mathematical description of his own particle change the instant his friend makes the measurement, even though no signal could reach him? Or does it only change when information finally crosses the light years to tell him? This is not a question of engineering, but of ontology. What exists and for whom? These mental exercises are tools for sharpening the mind. They do not provide easy answers, but they train us to hold contradictory truths in tension, preparing us for the ongoing, vibrant debates at the very foundation of what we call reality. They make the abstract tangibly, wonderfully puzzling, reminding us that to understand the quantum world, we must first learn to think in ways that feel, quite beautifully, alien. This abstract web of connection demands its own precise vocabulary, a new language for a new kind of reality. To truly grasp how scientists engineer spooky action, we must learn the basic grammar of quantum information theory. At its simplest, this field reimagines the universe not as a collection of things, but as a processor of information, with entanglement as its most valuable currency. The familiar unit of classical information is the bit, a definitive switch that is either a 0 or a 1. Its quantum counterpart is the qubit, a quantum bit. A qubit can also represent a 0 or a 1, but its true power lies in its ability to exist in a superposition of both states simultaneously, a ghostly blend of possibilities. This is where the magic begins, but the real transformation occurs when qubits become linked. When two qubits are maximally entangled, like the pairs in a Bell state, they share a fundamental resource measured in a unit called the EBIT. Think of an EBIT as a single, indivisible share of quantum correlation, the basic coin of the quantum realm. It is the fuel for protocols like quantum teleportation, where to teleport the state of one qubit, you must consume one EBIT of entanglement and also send two classical bits of ordinary information. This highlights a crucial rule known as LOCK, which stands for local operations and classical communication. It is the rulebook for what you can do with entangled particles when you are limited to manipulating your own local qubit and can only send regular, slower-than-light messages to your partner. Within these rules, you cannot create entanglement out of nothing, but you can manipulate it. This is where tools called quantum gates come in. These are the basic logic operations for qubits, the quantum equivalent of the and or gates in a classical computer. A specific set of gates can take independent qubits and entangle them, or it can transform already entangled states into different, useful forms. But the quantum world is noisy. Real-world entanglement is imperfect, degraded by decoherence into a weaker, mixed state. This is where a process called entanglement distillation becomes vital. Imagine you have a large supply of weakly entangled pairs, their connection fuzzy with noise. Through a clever lock protocol, you can sacrifice many of these imperfect pairs to distill or purify a smaller number of nearly perfect, maximally entangled EBITs. It is like filtering murky water to obtain a few glasses of pure, clear liquid. This entire framework allows researchers to treat entanglement not as a mysterious phantom, but as a quantifiable, manageable resource that can be generated, stored, transferred, and even spent. The violation of a Bell inequality, which once seemed a purely philosophical test, now serves as a benchmark for the quality and usefulness of this resource. When you hear scientists speak of achieving a high Bell violation in an experiment, they are not just proving quantum mechanics, they are reporting the fidelity of their EBITs, the readiness of their quantum fuel for a task. This shift in language, pioneered by thinkers like Benjamin Schumacher, empowers us to see the spooky action for what it has become, the cornerstone of a new technological paradigm, where information is written not just in zeros and ones, but in the deep, silent correlations between them. The equations of quantum mechanics feel timeless, but they were written by people with passions, doubts, and deep personal convictions. Behind the polished theories of entanglement lies a rich tapestry of human drama, a reminder that science is not a disembodied march of progress, but a profoundly human activity, shaped by friendship, rivalry, and moments of sheer, stubborn insight. The legendary debates between Albert Einstein and Niels Bohr were not merely intellectual exercises. They were a clash of worldviews conducted with a fierce, almost familial respect. Their arguments spilled out of conference halls and into long evening walks, continuing in personal letters for decades. Einstein, the revolutionary who had himself shattered classical physics, could not accept the inherent randomness Bohr embraced. Bohr, in turn, was driven to refine his ideas by the relentless sharpness of Einstein's critiques. Their relationship was a perfect entanglement of its own, each man's thinking deeply defined by the other's persistent challenge. While giants clashed, other key figures worked in quieter corners. John Bell, whose theorem would ultimately decide the debate, was not a celebrity physicist. He pursued his groundbreaking work while employed at CERN, focusing on particle accelerator design. His 1964 paper was a masterpiece of clarity, yet it initially drifted into relative obscurity, a quiet seed waiting for the right moment to sprout. It was the experimenters, the builders like John Clauser and later Alain Aspect, who rediscovered Bell's work and saw in it a blueprint for reality. When Aspect finally performed his decisive experiment in the 1980s, a journalist asked if he was nervous, testing the very foundations of physics. His reply was telling of a new generation's confidence. He said no because he knew quantum mechanics worked. His task was not to question the theory, but to expose the mechanism of the universe, to close the loopholes Einstein had so cleverly identified. The human stories weave through hardship and exile. David Bohm, a brilliant American physicist, was forced to leave the United States during the McCarthy era after refusing to testify before the House Un-American Activities Committee. He continued his work in Brazil and later London, and it was there, far from the mainstream, that he developed a sophisticated hidden variable theory, a direct descendant of Einstein's hope for a more complete description. His version of quantum mechanics, while non-local, showed that alternatives to the Copenhagen interpretation could be mathematically consistent. Then there is the poignant case of Erwin Schrödinger, the man who gave us the central equation of quantum waves and the famous cat. It was Schrödinger who, in a letter to Einstein, coined the German term Verschränkung, which translates to entanglement. He described it as the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Yet, after naming the beast, Schrödinger himself grew deeply uneasy with its implications. The phenomenon he helped define came to haunt him, a ghost in the machine of his own beautiful mathematics. As historian of science David Kaiser observes, these were people struggling with concepts that challenged their worldview. They were not mere logic machines. They were thinkers grappling with a universe that refused to conform to human intuition. Bell was motivated by a desire for clarity, Bohm by a search for order amid political chaos, Schrödinger by a philosophical disquiet. Their personal journeys, the fervent letters, the exile, the late-night worries add essential color to the stark black and white of the equations. They remind us that the long pursuit to understand spooky action was driven by the full spectrum of human emotion, by passion, curiosity, and sometimes a very human bit of stubbornness. This history does not weaken the science, it makes the triumph of understanding all the more relatable and inspiring, a testament to what we can achieve when we dare to question everything, even our deepest assumptions about reality itself. The entire cosmos we see today was once a space smaller than a single atom. In that unimaginably hot, dense beginning, the distinction between particles was meaningless. Everything was in direct contact, a seething quantum hole where entanglement was not a special link, but the default state of existence. This primordial web of connection was then stretched to a scale beyond comprehension by a brief but explosive period of cosmic inflation. In a fraction of a second, the universe expanded faster than light itself, and as it did, it pulled those initial quantum threads, those tiny fluctuations and correlations across the entire sky. The microscopic became macroscopic. The spooky action was woven into the very fabric of space. This leads to a staggering possibility. The pattern of galaxies, the vast cosmic voids, the entire large-scale structure of the universe might be the ghostly imprint of quantum entanglement from the first moments of time. The most important evidence for this lies in the oldest light we can see, the cosmic microwave background radiation. This faint, cold glow is the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. Embedded in its subtle temperature variations are the seeds of all future structure. Cosmologists meticulously analyze this map, looking for specific statistical signatures. The standard model of inflation predicts these variations should follow a Gaussian or bell curve pattern. But if multiple quantum fields were entangled during inflation, their correlated fluctuations could leave a distinctive non-Gaussian signature, a subtle twist in the statistics. As theoretical physicist Eiichiro Komatsu notes, inflation is a quantum phenomenon, so entanglement must have played a role. Finding these traces would be like discovering a cosmic fossil, proof that the quantum rules governing particles today also orchestrated the birth of galaxies. This idea pushes our understanding to the limit. It suggests that the spooky action we struggle to protect in our ultra-cold labs was, in the universe's infancy, the dominant force, a quantum glue that helped shape everything. The entanglement we now see across a lab bench is a faint echo of the connections that once spanned the entirety of creation. This cosmic perspective forces a profound shift. We are no longer just studying a curious quantum effect. We are piecing together the origin story of reality itself, where the quantum and the cosmological are revealed as one continuous narrative, written in the language of non-local connection.